Um, in today's lab, we first use the SciPy library for solving the ordinary differential equations. Then in the second part, the leapfrog method will be implemented. Uh, Unlike previous weeks, the simulation codes in this lab are implemented in Python. It is possible to run uh, scripts in a Jupyter notebook, or you can install Anaconda to conduct your experiments. Uh, let's start the first section of lab. In this example, we simulate the motion of two bodies circulating around one another under the force of gravity. The simulation is done based on Newton's equations, like the one we discussed in the lecture. The simulation code is shown here. This code concerns initial conditions and definition of gravity function that calculates the acceleration due to gravitational force between two bodies. Uh, in this code, m1 is the mass of the first body. x1, y1, and vx1, vy1 determine the position and velocity of the body m1 respectively. Similarly, the mass of the other body is equal to m2, and its initial position and velocity are x2, y2, and vx2, vy2. They are all initial conditions in this ODE problem. As you might notice so far, in this problem, we have totally 8 independent variables: x1, v1, vx1, vy1, x2, vy2, vx2, and vy2 are 8 independent variables in this problem. Here, initial values are collected together in the list y. So in list y, we have all initial conditions. If you remember in the lecture, I told that whenever we want to use a SciPy library to solve an ordinary differential equation, we should provide 3 items. The first one of those items is the vector of initial values y. As you can see here, we have listed all of these 8 initial values in a given list y. So list y represent this vector of initial values by 0. Here we have the definition of gravity function. Then here the function func defines the vector value user-defined function. This function corresponds to the function f discussed in this week's lecture. So here, as an input, we should have a vector value user-defined function f. And this is the function f. Here we have method solve IVP. This method solves Newton's equation. As we can see here, the method takes 3 input parameters: a vector valued function func. Uh, the initial and final target values for time. So time range between 0 and 50, and the initial values of the dependent variables y. So as I mentioned earlier, we have 8 variables, and those variables are listed together in y. So as you can see, we pass this y variable to this function to solve the Newton's equation. So as I discussed in the lecture, we should provide 3 items to the method to solve ODE, and as you can see here, we have determined all these 3 items in this solve IVP method. The output of this method will be some output values of y function. As you can see here, the output is some simulation values for y function, and the rest of this script is about plotting the motion of bodies. So as you can see here, we first have some initial condition, then the gravitational function, and to solve the Newton's law, we define the function f, and then we call the function solve IVP to solve the Newton's equation and obtain the position and velocity of the simulation environment, or the 2 particles we have in this simulation environment. Then, as promised earlier, in the second part of the lab, we are going to implement the leapfrog method in Python. In fact, in the second part of today's lecture, we are going to simulate the motion of bodies we discussed in the first part using leapfrog method. So in this implementation, in the second implementation, instead of calling solve IVP method, we solve the derivative equation using leapfrog implementation. As we can see here, this piece of code solves the differential equation based on leapfrog method, rather than calling the method solve IVP. It should be noted that this for loop implements the equation discussed in the lecture. So if you remember, here we discussed the formula for leapfrog method. This for loop iteratively implement this formulation and solve the Newton's equation. Okay, so that's all for today's lab. First, please go through the scripts to better understand what this script performs. Then you can run the simulation codes and play with different parameters such as step size h, mass m1 and m2. I don't know, you can play with different initial conditions to see how this changes the simulation output.